So, okay, so let's remember what we're doing. What are we doing? Anybody remember what we're talking about? It's been a long time. Much has happened. You've eaten much between the last class and this class. Diagonalization, yes. Say that again, Nora.
Oh, I said diagonalizing.
Yes, diagonalizing. Yes. Diagonalization, right? Diagonalization, right? So, right. So, what we said is that basically, if you're lucky, then your matrix is similar to a diagonal matrix, right? And lucky in this case means that you have a basis of eigenvectors, right? So right. So for some matrices, it's possible to find a basis of eigenvectors, and once you have a basis of eigenvectors, then it turns out that the matrix representation with respect to that basis is a diagonal matrix, right? And so your basis, your matrix, actually your linear transformation actually has a very simple way of behaving. Okay, so this is basically like a first step to understanding the behavior of linear transformations. Some matrices are very simple; they're diagonalizable. Yeah, Mariah.
But in the term of basis, they just have to be distinct.
Right. So what we said was that if you have n distinct eigenvalues, then you're guaranteed an eigenvector basis. Okay. But the opposite isn't true. It's not that you always have to have n distinct eigenvalues, right? Okay. If you have n distinct eigenvalues, you have an eigenvector basis. That's great. Okay. But that might not be the case. What we ended up with last time was this thing about geometric multiplicity and algebraic multiplicity. Right? Geometric multiplicity and algebraic multiplicity. And what we saw was that what did we see? Can anybody sort of say what we got last time?
The algebraic multiplicity is greater than
so that's one thing that we saw, that the algebraic multiplicity is always greater than or equal to the geometric multiplicity, right? And since remember that the sum of all the algebraic multiplicities equals the degree of the characteristic polynomial which we call n, right? We call it n. What this means is that the only way to be diagonalizable is if your geometric multiplicities are all equal to the algebraic multiplicities, right? The only way to have a basis of eigenvectors is if all geometric multiplicities equal the algebraic multiplicity. Right? Because if that happens, well, then you've got enough linearly independent eigenvectors to get an eigenvector basis, right? So, okay, so that's basically where we finished up, right? That your matrix is diagonalizable means that your geometric multiplicities are all equal to the algebraic multiplicities. Okay. So, yeah. So, I just want to say that this is kind of a first step towards understanding linear transformations. Right? So for some linear transformations, they're diagonalizable, and so their behavior is very simple. If you take a second course in linear algebra, you'll get to something called the Jordan canonical form. Which basically says that every linear transformation is basically is close to being diagonalizable. Okay, so like this gives you a complete answer, right? It's not just diagonalization that will work for some nice matrices. Okay, but it turns out that every linear transformation, every matrix, square matrix, is almost diagonalizable. You can get it into something called the Jordan canonical form. But don't worry about that. We're not gonna get to that. Okay. So today we're gonna go into 6.4, which is the topic is called Hermitian Matrices. Okay. Basically, this section is like some classic sum results in diagonalization. Right. So, like, what kind of matrices can you diagonalize? It turns out that there's a couple of classes that can be diagonalized. Yeah.
Is that one word or 2 words?
It's 2 words. Okay. Hermitian matrices. Okay. So I should say that today's lecture, is kind of a pretty simple one. So it's almost like we're starting off at the beginning again of another idea. Okay, and so it's going to be kind of slow for a bit. Okay. So these matrices are going to be complex matrices. So we're going to talk a little bit about complex numbers again. Let's recall, right? First off, let's recall that if z is a plus bi, a complex number, right, where a and b are real numbers, then we define z bar as a minus bi, and we call it the complex conjugate of z. Okay. Complex conjugate of z. We've seen that before, right? It's the reflection across the real axis, right? So you got z, you got z bar. Definition 2, we define the modulus of a complex number. We define the modulus of a complex number. It's just the same thing as the absolute value. Okay, modulus basically means absolute value. Yeah, Connor.
Is it the complex conjugate of z bar or z?
Ah, I'm sorry, that's just z. We define the modulus as the square root of z bar times z. Okay. Now, if z is a plus bi, then z bar times z is going to be a minus bi times a plus bi. Right? What's that going to be? A minus bi, a plus bi. It's going to be what's that?
Squared minus BI squared.
A squared, right? So it'd be the difference of squares, right? So that's going to be a squared minus b squared, I squared, but I squared is negative 1, and so we get a plus b squared. Right? I is the square root of negative 1. Right? So we get b squared times I squared, but b squared times I squared is negative b squared. Right? So we get a squared minus b squared. In other words, a squared plus b squared. So this is going to be the square root of a squared plus b squared. Right? And right. So if you have this guy a plus bi, then it's just the length. It's just the distance to the origin. Right? If this is a plus bi, then this thing here is a squared plus b squared. Okay, by the defendant. So it's just like back in the real numbers. The only difference is that you express it a little bit differently because we have complex numbers. Okay, so that's the modulus or the absolute value. Okay. We will consider vectors in Cn. Okay, we'll consider vectors where all the entries are complex numbers. Okay, so Z is going to look like, it's going to be a vector where all the entries are complex. Right? The Zi are all complex numbers. Okay. So complex vectors. We define the complex conjugate of a vector by just taking the complex conjugates of all the entries. So this is the complex conjugate of a vector. You just complex conjugate everything. Okay. Okay. Nothing exciting has happened, right? And that will continue. So we define the magnitude. We define the magnitude of a complex vector as you take the conjugate transpose of the vector, multiply it by itself, and then take the square root of that. You take the conjugate transpose of the vector times the vector and take the square root of that. Right? So what that's going to be, using this notation here, right? I'm going to get z1 bar, z2 bar, zn bar times z1 to zn, right? Everything to the 1/2. Right? And so that's going to be z1 bar z1 plus z2 bar z2 plus zn bar zn. Everything to the 1/2. Right? That's the same thing as the modulus squared, the sums of the moduli squared, everything to the 1/2. Okay. So it's just like in the real case. right? You take the absolute values of the entries, square them, sum them, and take the square root of that. Okay, it's just done with complex numbers now. Okay. Let me make a remark that in the book they use the following notation. They call Z conjugate transpose ZH. Z with a superscript H. Okay, and I think that's it's non-standard. I haven't seen this anywhere else, but at least I don't think it's standard. But it's a useful notation, so we're gonna use it. Maybe you can guess what the H stands for. What does the H stand for? Hermitian. Yes. Yeah. Okay. So, okay. We define an inner product on Cn. Okay, and here it is. The inner product of two complex vectors is going to be defined as WH times Z, the conjugate transpose of H times Z. Okay, so remember, in Rn, if we talk about one vector dotted against another vector, how do we define it?
V transpose.
Yeah, V transpose W. Right? So this is not so strange. Right? It's not so strange. What stands out about it is that we take W. We take W first, and we take the conjugate of W, right? We're taking the conjugate transpose against Z. Okay, so we're not just taking the transpose, we're taking the conjugate transpose. Okay, and so exercise show that this satisfies the properties of an inner product. Okay. You remember that to be an inner product, you had to satisfy a bunch of things. Okay. Now, the joke is, it's not an inner product. Okay? It's actually not an inner product. Can anyone see why this is not an inner product? There are a couple ways in which it fails. Right.
Like, isn't one of them, it has to be like alpha x plus beta y with z is like alpha x and beta z.
Yeah. Yeah, so you need linearity. Yeah. Yeah. And yeah, in fact, so this actually fails one part of linearity. So actually it doesn't. so notice it's not exactly an inner product. Because if you look, for example, if you look at, say, Z times alpha W, Z against alpha W, well, that's going to be alpha W conjugate transpose times Z. alpha W conjugate transpose times Z. Right? But you see the trouble, right? You don't get alpha, right? You don't pull out an alpha, you pull out an alpha bar, right? And you're left with, right? So right, you get alpha bar times the inner product. Okay, now you guys see that? Right, it's not linear. It's not linear in the second variable. Right. It is linear. It's actually linear in the first variable. It's linear in the first variable, but it's something called conjugate linear in the second variable. Okay, so this thing is conjugate linear in the second variable. Conjugate linear in the second variable. Okay, so it's not the inner product that we were talking about before. Okay, and so it's what we call, it is actually what's called a complex inner product. Okay, so it's okay. It's actually okay to have inner products that are conjugate linear in the second variable, but we distinguish between them and our old inner products. Okay, these guys are called complex inner products, and the other ones are actually called real inner products. Okay, so this is not a real, it is not a real inner product. It is it's in fact what's called a complex inner product. Okay. Abel, what is it?
No, it's like there's a third property for inner products.
Yeah.
That like when you multiply a vector by itself, the inner product of the vector with itself has to be greater than or equal to 0. Would that apply to?
Still going to work. Still going to work. Because look, when you multiply a vector by itself, what are you going to get? Right? When you multiply a vector by itself, notice that using our new notation, this is z against z to the 1/2. Right? Z against z to the 1/2. And you see that boils down to this number. But this is always greater than or equal to 0 unless all the entries are 0. Right? So that property is still okay. We've now checked it. Okay. Yeah. Yeah, the one that maybe should bother you more than that is what happens. Is it true that ZW equals WZ? The answer is no, right? Because this guy is going to be W conjugate transpose Z. This guy is going to be Z conjugate transpose W, right? There'll both be some number, but in fact they'll be conjugates of each other. Okay, so it's not equal. It'll actually be equal to the conjugate. When you reverse the order, you get the conjugate of the guy. Okay, but this is part of what we call a complex inner product. It's okay. It's not a real inner product. It's a complex inner product. Okay. So far, pretty simple. I hope. Right? I haven't really done anything. Complex matrices. Right. So you have n by n matrices where the entries are complex, and I think we did this before. For a complex matrix, we define its conjugate M bar as by conjugating all entries. Right, so you get complex matrix, conjugate every entry, and that will be the conjugate matrix. Okay, so now we get to a real definition. Everything else was just sort of rehash of things that we've seen before. I guess this may be considered that as well. So, if MH equals M, we say that M is a Hermitian matrix. So if M, remember this is M conjugate transpose, right? If M conjugate transpose equals M, and we say that M is a Hermitian matrix. Okay. What idea is this analogous to? Right. What definition is this the analog of for real matrices? Symmetric, right? Right? If this is a real matrix, what this is saying is that, right, M conjugate would just be M if this were a real matrix. So what this would be saying is that M transpose equals M, right? So it'd be a symmetric matrix. So a real Hermitian matrix would be a symmetric matrix. So symmetric. Symmetric matrices. Okay. Let me give you an example of what a Hermitian matrix looks like. Right? You got, for example, 1, 3 plus I, 3 minus I, 0. Right? This is a Hermitian matrix because if you transpose it, and you conjugate everything, then you get the same matrix. Right? Right? I take the conjugate transpose of this matrix, and I say that it's equal to my original matrix. Right? Because the 3 minus I becomes 3 plus I. The 1, when you conjugate, is 1. 3 plus I becomes 3 minus I. The 0 stays 0. How about what's up?
Would a joint be the same thing as the... If we take a Hermitian matrix, we're trying to find is the joint matrix?
It's not...
No.
No. Yeah, not the same idea. Okay. Okay, did everybody see that? Right? Everybody see that this is a Hermitian matrix, right? Because when you transpose it and you conjugate it, you end up with the same matrix. And what you notice about the Hermitian matrix is that, what do you notice about the diagonal elements?
They must be real.
They must all be real, right? Because they have to be equal to their conjugates, so they're real. Okay, so the diagonal elements are real. Okay. Okay, let's see how much time. Okay, so let me give you an exercise. If A is Hermitian, then Z inner product AW equals AZ comma W. So that is a Hermitian matrix, interacts really nicely with this complex inner product. And you can just slide it across the inner product. Okay. Think about that for a minute, and then we'll talk. I don't want to spend too much time on this. See if you can figure out. Just write out the definitions, right? What is this? What is this? And you'll see that they're equal to each other. Okay, talk to somebody nearby, just for a couple seconds. Let's get on with it. Nobody's talking? Nobody's talking? Let's do this. So what is Z? What's the inner product here? Z against AW? By definition?
It's Hermitian
AW H Z. Right? In other words, AW conjugate transpose Z. Right? And remember that the conjugate of a product is the product of the conjugates, so I'm going to break this up into two conjugates. Okay. We never proved it, but it's true. Okay. Then the transpose of a product, what's the transpose of a product? Right? It's a product of the transposes in the reverse order. Right? And so we get this. Right? Maybe I'll write it using the H notation. WH AH Z. Okay. Now over here, what am I going to get? WH AZ. Right? WHAZ. But that's what we got over here because A is Hermitian. Right? So this AH is the same thing as A. Right? AH is A, so they're equal. Right? Since AH equals A. So as long as your matrix is Hermitian, you can pass it through the inner product. Okay? What is it, Mariah?
Oh, no. This just came up in quantum mechanics all the time.
Oh, yeah?
Yeah, there's something special about being eigenfunctions with the same Hermitian operator. I don't remember.
Okay. Yeah, I'm afraid I never got that far in physics, regrettably. Okay, sorry. This leads to a theorem. Leads to the following theorem. If A is Hermitian, then when all the eigenvalues of A are real, all the eigenvalues are real, no complex eigenvalues. Okay. There's a term for the set of all eigenvalues. The set of all eigenvalues is called the spectrum of A. I'm just introducing this because next time we'll talk about something called the spectral theorem. Okay, number 2, eigenvectors corresponding to distinct eigenvalues are we actually had something like this before, right? Eigenvectors corresponding to distinct eigenvalues are linearly independent, right? Linearly independent. That we had before. So that we know already. But for its Hermitian, it's in fact better. They are orthogonal. Okay. So it's something stronger happens if your matrix is Hermitian. Do you guys have a question? I'm gonna ask.
Oh no, it's just like the theorem it says A as a real matrix n by m.
Yeah, that's true. Why don't we do all this based on the complex?
What am I doing? Thank you.
Sorry.
But so A has to be square.
Yeah, it has to be square. Because otherwise you can't talk about eigenvalues and eigenvectors, right? Because it would be going from one space to a different space. Right, so there would be no eigenvectors. Thank you. Yeah, I had the C in my notes, but I just didn't notice it. Okay. Okay, so let's prove this. We're actually going to prove this using the property of Hermitian matrices that we just proved. So proof of 1. Right? We want to see that all eigenvalues are real. Okay, so suppose that V is an eigenvector in some eigenspace. Okay. In other words, AV equals lambda V. We want to show that lambda has to be a real number. Lambda has to be a real number. Okay. And the way we do it is by considering the following. The inner product of V against AV. Okay. So by what we just saw, that's the same thing as the inner product of AV against V. Right? But AV, remember, is lambda V. AV is lambda V. And then by conjugate linearity, when we pull out this lambda, we're going to get lambda bar times the magnitude squared of V. Okay. Okay. Now, what's going to happen on the other side? We're going to do the same thing, but we have lambda V here. And we pull out the lambda, and we get lambda times the magnitude squared. Right? Okay? Right? And so remember that this guy is non-zero, right? So the magnitude is non-zero. Oops. The magnitude is non-zero. And so you can cancel out, you can divide both sides by the magnitude, and you get that lambda bar equals lambda. And you divide both sides by the magnitude squared, and you get lambda bar equals lambda. Okay, Everybody all right? Can you see that? Okay. Second part, want to see that eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, so you say, okay, well, suppose that V1 is in one eigenspace and V2 is in another eigenspace. Okay, and that lambda 1 and lambda 2 are different. Okay. We're hoping to see, want to show that V1, V2 is equal to 0. Okay. Okay. The argument goes pretty similarly. If you look at A, V1, V2, again, by what we saw before, this is the same thing as V1 times AV2. Right? Okay. So what's going to happen? What do we get here? V lambda 1, V1, V2. What do we get here? We get V1 against lambda 2, V2. Right? We pull out the eigenvalue and we get V1 against V2. And we pull out the eigenvalue here, and what do we get? We get the conjugate. We get the conjugate, V1, V2, right? Which seems to be not exactly what we want, but then we remember that by part 1, all the eigenvalues are real, right? So lambda 2 conjugate is just lambda 2. Right, so we get lambda 2, and so you get this, right? Lambda 1 V1 V2 equals lambda 2 V1 V2. Okay, and that implies that V1 V2, oops, must be 0. Because if not, you can divide both sides by 0 and get lambda 1 equaling lambda 2. But we know that lambda 1 and lambda 2 are different. Right? So V1, V2 has to be equal to 0. Because lambda 1 and lambda 2 are different. Okay. So this is cool, right? It's not just that the eigenvectors are linearly independent. They're actually orthogonal to each other. They're perpendicular to each other. Okay. So, any questions? Everybody okay? It's pretty straightforward. There's a corollary. Actually, let me introduce the definition before I state the corollary. Okay. So if you have an n by n complex matrix, if the columns of U form an orthonormal set, orthonormal basis of Cn, with respect to the complex inner product, we call U a unitary matrix. A unitary matrix. Okay. So this is the analog of the orthogonal matrix. Right? Do you remember the orthogonal matrix that we wanted to call the orthonormal matrix? Right? The columns formed an orthonormal basis. So if you've got a complex matrix whose columns form an orthonormal basis with respect to the complex inner product, then we call that guy a unitary matrix. So now we can see the corollary. The corollary says this, that if A has n distinct eigenvalues, then what? Right. Then you can find a basis of eigenvectors that are orthonormal. Right? Right. Then you can find a orthonormal basis of eigenvectors. That's not this part of the statement. Let me just say, then there exists a unitary matrix that diagonalizes A. That's basically the proof, right? That's the reasoning, right? By the theorem, you're going to get this orthonormal basis of eigenvectors, and you use them as put them into a matrix, and that matrix diagonalizes A. Okay. So there'll be a matrix where all the columns are eigenvectors. They're all orthogonal to each other, and they're all unit vectors. And so it's not just diagonalizable. It's diagonalizable in a special way. It's what's called unitarily diagonalizable, okay, if you want to say that. Okay? Okay, sorry, I should not say that. If A is Hermitian, and has n distinct eigenvalues, then it's unitarily diagonalizable. Okay. Next time, we'll see the spectral theorem, which says that any Hermitian matrix is unitarily diagonalizable. Okay. Any Hermitian matrix is unitarily diagonalizable. That should be really shocking to you, right? Like, it's not like you have to have n distinct eigenvalues. The eigenvalues could be whatever they feel like, okay? Right? Any Hermitian matrix is unitarily diagonalizable. That's going to be a heck of a proof. It may take 2 days. Okay. You may want to look at the proof before the next class, just to prepare yourself somewhat.